Hello, everyone, and welcome to our next edition of the Extremal and Probabilistic Combinatorics webinar. Let me remind you, this talk is being recorded and we will put it on YouTube later on. If you have any questions, then please either just unmute yourself and ask it, or if you have a problem with your audio or you don't want to be recorded, then just write it in the chat, and either our today's speaker notices the question, or I can read it out. And so now it's my, oh, and you can find slides for today, yes, on our webpage, and they are now also linked in the chat. And now it's my pleasure to introduce Vishesh Jain from Stanford, and Vishesh will talk about the Lovász local lemma. So Vishesh, please.
Thank you so much, Jan, for the invitation, and also to all of the other organizers. And thanks everyone, from all over for joining the talk. So today I'm going to talk about some recent work in computer science, but I hope this fits the probabilistic part of extremal and probabilistic combinatorics for this webinar. So this is joint work with Huy Pham and Thuy Duong Vuong. She goes by June, and both of them are graduate students at Stanford. Huy is a graduate student in math, and June is a graduate student in CS, right? So oh, wow, I can't. Okay, let's see. Good. Okay, so let me just sort of introduce some setups. So this is, the usual setup of the variable version local lemma, but just a sort of setup notation here. So x1 through xn are going to be independent random variables with finite support. C1 through Cm are some collection of bad events. So for the purpose of this talk, you should think of Ci as the event that some constraint I is violated, right? So we will think about instances of Lovász local lemma as constraint satisfaction problems. So the variables are xi's and the constraints are CJ's, right? Okay, so Ci bar is the complement of Ci. Okay, this is a little silly, but just to say that I'm not using Ci subscript C. Pi is the probability that Ci is violated. P is the maximum probability that any clause is violated. In the usual setup of the local lemma, recall what we do is we say, well, each constraint depends on some set of variables. So variable Ci is the set of variables that the constraint Ci depends on. And when you have this thing, the standard thing to do is to just draw the dependency graph. So in the dependency graph, what you do is the vertices are the constraints, and then two constraints are adjacent if they share a variable, right? And the key parameter in the local lemma, as you recall, apart from the things that I've mentioned, is the maximum degree of the dependency graph, and this I denote by capital delta. And here I say that okay, E is actually the base of the natural logarithm and not the number of edges, right? So it's 2.71, but really think of it as 3, right? Okay, so I'll try to sort of I mean, yeah, the results are not going to be sharp, so this is like not going to play a role, but it's just to say that if you see an E somewhere, it's 2.71. Okay, so this is the basic setup of the local lemma. I hope it's clear. If not, you can ask questions about the notation. But let me just sort of recall what the symmetric Lovász local lemma is. So this is the variable version form of the symmetric local lemma, and of course, like there are many experts here, and that there are like much more general forms, but we will not talk about those. We will just sort of deal with the most basic symmetric version of the local lemma. And what this says is that if E, okay, this 2.71 times the maximum probability of any constraint being violated, times essentially the maximum degree of the dependency graph, right? If this is at most 1, then you can actually find then with positive probability there is an assignment to the variables which satisfies all of the constraints. So this is just the event intersection of Ci complement, and in fact it even gives you some sort of quantitative estimate on what this probability is, right? So not only is this probability strictly bigger than 0, but there is some lower bound on this, and this is okay. So I'll call this the LLL condition. But of course, as many of you know, that there is a sharper condition availability to sharer, and then there are sort of non-symmetric form. So there's the asymmetric form of the local lemma, there's the lopsided local lemma, and there's like a whole body of work on this, right? But we will sort of restrict ourselves to the simplest thing because even with this, even for the simplest form, there are questions that we cannot answer, right? So I'll just sort of restrict myself to the simplest form. Okay. Okay. So just to sort of go towards at least sort of have some concrete instantiation of this thing. So a Boolean KC and a formula is just something which is an AND of ORs, right? So again, this is a constraint satisfaction problem. So each of the constraints is some, so it's a, so okay, here I wrote down a 3CNF formula. So I have a bunch of constraints, and each thing within the parenthesis is a separate constraint. And then you're asking that, okay, all of these constraints are satisfied. And then the constraints are something like, for instance, the first constraint is x1 or complement of or not x2 or x3. So this is, there is exactly one assignment which violates it, and there are 7 assignments which satisfy, right? So this is an example of a 3CNF formula. And you can replace 3 by k, and then you get a KCNF formula. A special class of KCNF formulas are the so-called monotone CNF formulas, and these are just formulas which don't have negation, right? So all of the literals just appear as R's. And now from the point of view of satisfiability, this is rather trivial, because for instance the all once assignment is a satisfying assignment of this thing. But we will see that from the point of view of what we are talking about here today, which is sampling or counting, this is already like non-trivial, and this is already a hard thing to do. Okay. So I said that for the monotone CNF formula, of course, the all once assignment is a satisfying assignment. For a general KCNF formula, so not necessarily monotone, the Lovász local lemma tells you that there is a satisfying assignment, provided that let's say delta plus 1 is at most 2k over e. If you now you're a little bit upset, you're like, okay, this is not the right answer, so this is true. So if you use the lopsided version of the local lemma, you can improve this bound by another factor of 2. So instead of 2k over e, you can get 2 to the k plus 1 over e. And this is actually asymptotically typed, right? So you can construct instances of this thing such that this condition is not met and you don't have a satisfying assignment. So this is I guess, okay, it's not as classical, and this is only from 10 years ago, right? Okay, so this is sort of the example of the KCNF formulas, and this is sort of classical application of Lovász local lemma in computer science, where you say, well, this tells me that CNF formula has a solution, and it tells you when it does. Okay. So I hope that this thing is familiar to many of you, and if not, then this is some sort of introduction. Okay. So of course, with the Lovász local lemma, this is an existential statement. It tells you that a solution exists to your constraint satisfaction problem under this condition. So let's say KCNF formula, delta plus 1 is less than or equal to 2k over e, and I know that a solution exists. And now from an algorithmic point of view, the first question is, can we actually find such a solution, right? So the first thing that you might try to do is you might just try to use rejection sampling. You say, well, the Lovász local lemma tells me not just that a solution exists, but it tells me if I flip a coin for each of my variables, then there is a positive probability of the solution of finding the solution. And unfortunately, this positive probability is exponentially small, right? So it's exponentially small in the number of constraints. So if you just use rejection sampling, and rejection sampling is you sort of just generate a sample, and if it doesn't work, you generate the sample again, and if it doesn't work, you keep doing it. Then in expectation, you need exponential time to even get one hit, right? So this is not an efficient way of doing things. However, this is a long line of work that there are efficient algorithms for finding satisfying assignments. And the first result in this direction was due to Beck in the 90s, so early 90s, 91. So he showed that, okay, not quite under the Lovász local lemma condition, but if you have sort of a Lovász local lemma type condition, right? So the k is replaced by k over 48, then you can actually find a satisfying assignment efficiently. And then this 48 was improved, in a series of work. So there was work by Noga alone, so improving from 48 to 8. And then there were a couple of intermediate works, but I'm not like totally sure if they got a better constant for this CNF problem, like KCNF problem. So I apologize if I've omitted something that I should have mentioned. But sort of, the last work along this line was by Srinivasan, and who sort of pushed these techniques to, give an algorithm for finding a satisfying assignment under this condition 2 to the k over 4, right? And after that, if you know how the story goes, you know what happened. So first there was, a work by Moser, pushing beyond this 4. So we'll see today where this 4 comes from, and this is sort of, a fundamental obstruction to the sampling problem as well that we have. But anyway, Moser was able to push beyond this to get a 2. And then Moser had another paper where he was able to get 2 to the k over 32. So get the correct exponent, but for the suboptimal constant. And then there was the celebrated work of Moser and Tardos, where they got the correct condition. And of course, if you know about this work, they also have an algorithm for the asymmetric version of the local lemma, under some mild conditions. And in fact, the thing with the Moser and Tardos algorithm is that it doesn't really use the local lemma as a statement itself. So this provides like a new algorithmic proof, right? And then there's like a whole line of research after this. There are people who want sort of algorithmic versions of like Shear's form of the local lemma, algorithmic versions of the lopsided local lemma, and there's like a whole line of work which frankly I'm not an expert in these things, so I'm missing stuff here, but you can Google algorithmic Lovász local lemma and you'll find a ton of things. So this is sort of the existential problem, and in some sense, at least for like the most basic forms of the symmetric and asymmetric local lemma, this is something that's totally settled, right? We have the condition of the Lovász local lemma, and then we have the algorithm, right? Okay. So the question that okay, so even though my talk is called towards the sampling Lovász local lemma, I'm going to talk about counting, and if you know these kinds of things, that these are basically equivalent for self-reducible problems, right? So approximately counting and approximately sampling is essentially the same thing. And okay, so now you can ask the question. You can say, well, great, we have all of these great works on the existential algorithmic Lovász local lemma. Under the Lovász local lemma condition, can we approximately count the total number of satisfying assignments, right? So this is okay. This is not even for instance, for the monotone case, right? So the monotone case, there's nothing to do existentially, right? There's the all once assignment. It's satisfying, but okay, can you count the total number of satisfying assignments? I mean, this is like like finding like independent sets in hypergraphs, right? Basically, I mean, you have exactly sort of the all once assignment, the all zeros assignment is sort of the violating one. So now if you switch the rules of ones and zeros, you're basically counting independent sets in hypergraphs. So it doesn't seem like it doesn't seem that easy. And indeed, yeah, okay. So some, perhaps if you're like, very optimistic about algorithms, then this might come as a surprise that no, you can't do this thing. You can't count. And what do I mean by no? So this is, like under standard complexity assumptions, right? So in this case, it's NP hard to count even approximately the total number of satisfying assignments, right? To a KCNF formula. Even if you change, delta less than 2 to the k to delta less than 2 to the k over 2, right? So you weaken this thing quite a bit. And even if you demand that the formula is monotone, right? So an instance which is trivial for the existential thing is actually hard for the counting thing, right? And since this might seem like very, very surprising, so let me just sort of give at least like a very, very small sketch of the reduction. So if you're bored for the rest of the talk, you can work this out as an exercise, at least a reduction, right? Okay. So the idea is there is a famous line of work started by Sly and then Sly Son and others, where they show that approximating the partition function of the hardcore model on a delta regular graph is NP hard if the fugacity is above this critical thing, right? So I just want to remind you that the hardcore model is a distribution on the independent sets of a graph where the probability of having an independent set is proportional to lambda raised to the size of the independent set, right? So if I is an independent set and I has size 6, then the probability of I is proportional to lambda to the 6, and the partition function is just the sum of the probabilities, right? So it's a normalizing constant, and this line of work in the early 2000s, it shows that approximating the partition function of the hardcore model on a delta regular graph with fugacity which is larger than this critical thing is NP hard. And now the reduction is not so hard. So what you do is if you have a delta regular graph G, so you think of like having a hard instance for this problem, what you can basically do is you can construct a uniform hypergraph where every vertex has k copies, And then every edge is just going to be sort of, the concatenation of the respective k copies, right? So if UV is an edge in the graph, then, U1 through UK prime and V1 through VK prime is going to be an edge in the hypergraph. So now this gives me a 2K prime uniform hypergraph. And now you should think about that there's sort of a natural way to map independent sets of the hypergraph to independent sets of the graph. Namely, if I have an independent set of the hypergraph and, there is some vertex and all of its guys are occupied, so all of its guys are 1, then I also occupy it in the graph. And then, if you think about it for a second, you'll see that there is a correspondence between, independent sets of the graph and independent sets of the hypergraph. And then this K prime guy is controlling the fugacity of the model. So, you can cook up a collection of parameters such that, if you can find the number of independent sets of the hypergraph, you can, compute or approximate the partition function of the hardcode model above a sufficiently high fugacity, right? So this is, if you didn't follow this, I mean, this is totally fine. This is a sidetrack for the talk, but, I just sort of wanted to give you a sense of how you might even prove something. And, okay, this follows from, the kind of like models which I've studied. Okay. So now you might say, okay, this is kind of bad news, and we have this NP hardness result. So what can we do? So now you change the question. You say, well, okay, I'm going to relax my assumption a little bit, and I'm going to say if I have a Kc and a formula, and delta is less than or equal to 2 to the k over 2, right? So when I say less than sim, I'm omitting constants here, right? So none of the results that I'm going to discuss are sharp. So I might as well just omit constants here, right? Okay. So okay, the question is that okay, now if I have a Kc and a formula, and the maximum degree is at most 2 to the k over 2. Can we approximately count the total number of satisfying assignments, right? So, Hermann and Zhang in 2016, they showed that yes, this is true, provided that the formula is monotone, right? So in this case, which was which is basically hypergraph independent set, they show that you can indeed do this thing. And indeed, in fact, what they show is that the Glauber dynamics on the independent sets, this actually mixes in time n log n, where n is the number of vertices. So this actually gives you a fast sampling algorithm, and then you can use the correspondence between sampling and counting to also get like a counting algorithm, right? So in the monotone case, this is known, and I mean this is I want to emphasize that the monotone case is not trivial because the NP hardness example that we have is also for the monotone case, right? So monotone cases are hard, and their result sort of meets the NP hardness threshold up to a constant. But this is still doing it for the monotone case. Okay. So what about sort of general things? So there is this work of Guo, Jeremy, and Liu in 2016. So they came up with this idea of perfect sampling called partial rejection sampling. So if you know about this, for instance, sync popping, cycle popping algorithms, then this is a generalization of that line of work. And what they showed is that, well, if you have like sort of, if your formulas are sort of extremal in some sense, or if either like clauses don't overlap or they overlap a lot, so some sort of extremal conditions, then you can use this partial rejection sampling framework, and you can actually sample either like up to the hardness threshold or like the entire Lovász local lemma threshold, right? So the point is that okay, this is these are some sorts of instances with some special combinatorial structure. Okay. Now you can ask, okay, what about general Kc formulas, right? So I don't demand monotonicity, and I don't have like any particular structure. So here the first work, at least as far as I know, is due to Ankur Matra, and he has like a new way, and we'll see this today. So he has like this sort of new deterministic algorithm, which actually works until like okay, delta is less than or equal to 2 to the k over 60, right? So 60 is some constant, and the point is that okay, this algorithm is sort of efficient in the regime where the uniformity of the formula is order 1, right? So the point is that the running time as opposed to like Glauber dynamics, it sort of blows up with the maximum degree of the dependency graph. So all of this is sort of more of theoretical interest, and these algorithms are efficient polynomial time when the uniformity of the hypergraph is, or the maximum size of any constraint is order 1. And this was improved in a couple of works. So there was this work first by Feng Guo, Yin, and Zhang, and then by Feng He and Yin. And what they did was okay, they had like improvements in 2 directions. So firstly, they were able to sort of improve this 60 to 13. So that was one thing. And the other thing that they were able to do is they were actually able to give sort of a fast sampling algorithm. So a sampling algorithm, which is actually polynomial in K, as opposed to sort of exponential in K, right? Or I guess this guy is more like doubly exponential in K, right? Because delta is like 2 to the K, and this is n to the poly delta, right? So anyway, the point is that, these are sort of, the other algorithms are faster algorithms. And, these are actually things that you can implement. So that's nice. And then the other thing is that, the bound is closer to sort of what the truth is. One thing I should say is that, there is, some difference between the two, which is that, the running time of Ankur's algorithm is slower, but it's a deterministic algorithm. And if you know about, these deterministic approximate counting things, then these kinds of running times are, what people typically see, right? So you do have sort of, these bad running times depending on some parameters. So, it's kind of par for the course in that sense. Okay. So now you might say, okay, yeah, we said something about, KCNF formulas. Okay, this is one instance of the local lemma, and, now we've said something about it. So what about, other, so for instance, we say that this algorithm of Moser and Tardos, this works for like, basically any instance of the local lemma. So can you say something about, instances of the local lemma, which are not KCNF formulas, right? Okay, so the next, thing which, is a natural thing to consider is, for instance, proper coloring of K-uniform hypergraphs, right? So, this is just, I have a K-uniform hypergraph. To every vertex, I assign a color, and I want that no edge is monochromatic, right? Okay, cool. So, if you use the local lemma, just directly, so for the uniform distribution on colors for every vertex, then this shows that, if Q is, bigger than, if the number of colors is bigger than the degree of the hypergraph to the 1 over K minus 1, then I'm guaranteed to have a coloring. And, there are some constants here which I'm omitting. And, what again, Guo, Liu, Lu, and Zhang showed was, okay, if you replace 1 by 14, then you have a deterministic algorithm. And, this is sort of, like building on Ankur's method. And then again, this work by Feng, He, and Yin, this sort of improved it in two ways. First, it got the 14 to a 9, and then, it got, it has this sort of faster running time. But again, there's the difference between deterministic and approximate. But yeah, I mean, you see, like, the constants are kind of far up, right? There's like 1 versus 9, and it's sort of stuck here for like in their work for, I mean, they tried optimizing it. Okay, so now you might say, okay, okay, I've seen 2 examples. I've seen KCNF formulas. I've seen Q coloring. Okay, now are you actually going to just, prove a theorem for like every particular problem I give you? Okay, so now you try to sort of do something more general. So if you sort of, try to generalize these previous works, then the natural thing to look at are sort of constraint satisfaction problems, where every constraint is violated by like a very small number of assignments to its variables, right? So in the KCNF formula, it's exactly 1 assignment. In Q coloring, it's exactly Q. So, okay, you say, well, to start with, let me look at these so-called atomic constraint satisfaction problems. And these are, just like CSPs where, every constraint is validated by exactly 1 assignment. So here, what these guys, Feng, He, and Yin show is that, okay, for like even a worse constant, right? So delta to the 350, right? So the local lemma would be something like P delta is less than or equal to 1. And here, there's a condition which is P delta to the 350 less than or equal to 1. And they show, well, okay, so you can like do these fast sampling algorithms. And, like one thing which is, okay, like maybe something you don't appreciate initially, but the point is that, here, even though sort of, the running time depends on things like, the size of the constraints and, like the size of the alphabet, the actual condition does not. So in that sense, it's closer to, like the actual symmetric local lemma condition, which is, really a condition like P delta less than or equal to 1, and it doesn't really care about, the uniformity of the instances, right? So in this sense, this is sort of more of a pure local lemma kind of condition. Okay. So now you might ask, okay, what about constraints which are, not atomic? Well, okay, the naive thing to do is say, well, if I have a constraint satisfaction problem in which every constraint is violated by n assignments, I can, of course, write it as an atomic constraint satisfaction problem, right? Just by sort of replicating each clause at most n times. And then, this becomes an atomic constraint satisfaction problem. Okay, this seems too good to be true. Well, the price that I pay is the degree, right? Instead of having degree delta, the degree blows up to n times delta. So now, if I plug it into this previous result, what this is going to tell me is that if, P n delta to the 350 is less than or equal to 1, then I can, like efficiently, count and sample assignments. Okay. Just to sort of see that this is not a good condition, So imagine, we have the case where, the variables are Boolean and each constraint has exactly k variables, right? So in this case, P is going to be 2 to the minus k, right? In the atomic case, right? There's one validating assignment and that happens with probability 2 to the minus k. So, this result, this previous result is not going to give you anything non-trivial if n is bigger than, 2 to the k over 350, right? It doesn't give you anything at all because, it sort of cancels out and becomes 1 on the left-hand side. But, if you do probabilistic combinatorics, the way sometimes or often the way you use the local lemma is, as a replacement for Chernoff plus union bound, right? So instead of Chernoff plus union bound, you do something like Chernoff plus local lemma. And, if the probabilities of your bad events are being controlled by concentration inequalities, then n is going to be much larger, right? Like if you use Chernoff, then the probability of the violation is going to be 2 to the minus k over 3 or something. So n is going to be much larger, right? N is going to be on the order of 2 to the k over 2 or something. So unfortunately, this scheme of decomposing is bad for the kinds of things you see in probabilistic combinatorics. Okay, so this is I think what I want to say about the background. Now, as for our results, so the first thing we show is that for general constraint satisfaction problems, right? So there's no no sort of atomic thing or anything. So if I have a general constraint satisfaction problem, and forget about this q squared k thing, right? This is meant order 1. Anyway, the running time blows up otherwise. So basically what we show is, if you have a general constraint satisfaction problem and P delta 7 is less than or equal to 1, then there is a deterministic algorithm to approximately count and sample the total number of, deterministic algorithm to approximately count, and then, a randomized algorithm to sample. In fact, you can perfectly sample from the distribution and satisfying assignments. And, just sort of as consequences, for KCNF formulas, this works up to, k over 7. And for Q colorings, this works for, colors which are bigger than delta to the 7. So this improves from the previous bound, which was 13, and here there was a 9. But, it's still kind of far off from, what the truth is. But I guess sort of the nice thing is that, we'll talk about the proof a little bit, and you'll see where the 7 is coming from. So at least, now there is a clean reason for where the 7 comes, and, you can sort of hope to, incorporate sort of newer tricks and, push this towards 2 or something, right? So I hope I can talk about the proof just a little bit at least. Okay, so now you might say, well, this is still kind of far off, and moreover, your running times are bad. So okay, this is of theoretical interest, but what about sort of instances I care about, like SAT or Q-coloring hypergraphs or something? Okay, so the best result we have here in terms of constant is really for Q-coloring K-uniform hypergraphs. So here we show if Q is bigger than or equal to delta to the 3, basically delta to the 3 over K, then you can you have this fast algorithm for counting and sampling Q colorings of K-uniform hypergraphs, right? So now this 3 is actually not so bad because it's conceivable that actually 2 might be NP hard, right? So I mentioned that in the KCNF formula case, right, there is this NP hardness at 2 to the K over 2. In the Q coloring case, this is not known because the reduction doesn't quite work. But it's conceivable that the Lovász local lemma threshold, which is delta to the 1 over K minus 1, is actually sort of beyond the reach of algorithms, and there is actually some other constant, right? But this we don't know. But sort of if it turns out, for instance, that this is 2, then okay, this is some level off, and you can kind of see where the losses are coming. I mean, these are sort of the same sorts of losses that are in this line of work due to Beck, which was refined by Alon and then Srinivasan, right? So this is sort of the combinatorial barrier that we're stuck at, and sort of in the SAT case, what we can show is that okay, the 7 that we have, you can improve this to 5.71, and this 5.71 comes from some numerical optimization of some optimization program with KL divergence and so on. Okay, so it's 5.71 versus 2, and we're kind of stuck here. So it would be great to sort of push it towards something better. I mean, for this thing, I think the 3. So the 5.71 is okay, it's whatever, right? The 3, we actually try to optimize this quite a bit. So I think even something like 2.99 would be kind of interesting because I think you would need some new idea on top of here, and presumably if you can get 2.99, maybe you can sort of push it all the way down. Okay, and finally, in this question of sort of okay, can you do something for like a pure Lovász local lemma type condition? So recall, I mentioned this result with like p to the delta 350 less than or equal to 1. And, like if you sort of do these things correctly, we can basically get like a 7 here as well, right? So yeah, so these are sort of results. I mean, it's basically, I mentioned like a bunch of numbers, which may or may not make any sense to you, but this is kind of boring, right? But I'll start talking about proofs a little bit now. But in case anybody has questions about like what we're trying to prove here, what the results are, now might be a good time to ask. Okay, so if not, so here's sort of the plan for the rest of the talk. So what I want to do is, I want to discuss some of the ideas behind this deterministic p delta to the 7 less than or equal to 1 result, because I think this is sort of like the cleanest constant that's showing up, and you can, okay, other than the 3, but this is easy to discuss. And I hope it seems to me that this should be, you should be able to improve this if like using some like couple of like combinatorial tricks or like ideas. So for simplicity, what I'm going to do is I'm going to discuss like a slightly worse version of this thing, where instead of 7 you have a 10, and going from 10 to 7 is just like some sort of averaging argument that you have to carry out carefully, right? So the disclaimer is that this is the first time I'm giving this talk, and this might be a total disaster. So what's going to happen for the rest of the talk is there is one part that's understandable, and this is sort of basically Beck's proof of the algorithmic local lemma. And this, I hope that if like you're young like me, and the first proof of the algorithmic local lemma that you saw is Moser and Tardos, then you will see this classical proof of Beck, and this will be some nice math, and that'll be good. And then provided we have time, I will show you some of the ideas to get the counting version using these ideas. And like if you run out of time and you want me to stick around, I'm also happy to talk, and I also have slides up. Okay. Anyway, so let me sort of talk about Beck's approach to the local lemma. So there are probably many people in the audience for whom this is very familiar, and some people for whom this is new. So the approach that Beck had to the algorithmic local lemma was sort of 2 steps, right? So the idea was first to sort of find, use like a randomized greedy process to find some maximal good partial assignment. And then the second thing was to sort of extend this good partial assignment to a complete assignment, a complete satisfying assignment. And what does he mean by good assignment, a good partial assignment? So a good partial assignment means 2 things. So firstly, okay, well, you should be able to extend it to a satisfying assignment, right? This is sort of like the lowest bar you can have for a good partial assignment. The second thing, which is really the crucial thing, is that you say, well, if I have a partial assignment, what's going to happen is that some guys are already satisfied, and then there are some guys which are not yet satisfied, right? So for instance, if you think about like k-set, what's going to happen for k-set is that some guys are already satisfied, right? Because as soon as like one of the literals is satisfied, then this is satisfied. So I can throw away this clause, and then there are constraints which are not yet satisfied. So what you do is you sort of look at the line graph of the constraints that are not yet satisfied, right? So you have the vertices which are constraints which are not yet satisfied, and they intersect if they share a variable. And what you want to show is that the line graph of the not yet satisfied constraints is logarithmic in size, right? And the reason that this is useful is that now if you have this good partial assignment, that this can be extended to a complete assignment. And what's happening is that the formula is decomposing for all of these connected components, right? Like if 2 variables are in different connected components, then they can't really influence each other through like any of the not yet satisfied constraints. So what you can do is, you can just search exhaustively, you can just do exhaustive enumeration in each of the components. The components are of logarithmic size. So exhaustive enumeration takes time, 2 to the log n, which is like polynomial in that, right? So this is kind of the idea that, find a good satisfying assignment such that, the unsatisfied clauses, factor into logarithmically sized components, right? So this is the idea. And the way you do this is, okay, so now you want to do this, the main thing is to sort of show that, with high probability, you will have this, good assignment. And how do you do this thing? So this is sort of the randomized greedy procedure, right? So it's kind of, the natural thing that you might do. So, okay, so first what you do is you order the variables and order the constraints. And now what you do is, initialize, okay, you sort of partition the variables into available variables, assigned variables, and frozen variables, right? So initially everything is available, nothing is assigned, and nothing is frozen. Okay, now what you do is you take the first available variable and assign it a random value, right, from its alphabet. And well, once you do this thing, then this variable is no longer available and it's assigned. So you have to move it from available to assigned. Okay, so you do this thing, right? Now, the key thing is what you do is you have like a threshold for the conditional probability of violation of every clause, right? So initially, you know that each clause each constraint is violated with probability at most p. And you say, well, you know, a clause is kind of dangerous if, you know, the conditional probability of violation, you know, conditioned on the assignment I have right now, exceeds p prime, right? You know, p prime is going to be bigger than p, right? So once this happens, you say, well, you know, now these constraints are dangerous. And what you do is, you know, like you say, well, you know, this guy is looking like it's going to be violated. So I'm not going to assign any variable which appears in such a constraint, right? So what you do is, you know, you just freeze all of these guys. And, you know, then you know, you just sort of repeat this process, right? So this is kind of the natural thing, you know. It's a randomized greedy thing where you just kind of keep assigning variables until it seems like, you know, a variable is in a clause, which is, you know, like already sort of exceeds my risk threshold for violation, and then I freeze it, and then I just continue this process, right? So this is sort of the algorithm. Okay. So yeah. So any questions about like the process, and then we sort of discuss why this works. Okay.
So what happens to the frozen variables?
So they are just not assigned. So that's why the assignment is a partial assignment. So I just like assign them. So the hope is that the frozen variables are going to be assigned with the exhaustive enumeration at the end, but I'm not going to do like the random assignment for these guys. Yep. Okay. So now I want to show that this is a good partial assignment. So I kind of need to show two things. One thing I need to show is that this partial assignment can be extended to a complete satisfying assignment. And for this, you can appeal to the local lemma, right? So for the local lemma, you know that if P delta is, so okay, so now the clauses that are remaining, right, their conditional probability of violation is P prime, right? Because that was my error threshold, right, my risk threshold. So now, you know, if P prime delta is less than or equal to 1, then by the Lovász local lemma, I know that the partial assignment can be extended to a satisfying assignment. And this, as Wojtek said, is like, okay, what do I do now? Now I can find it by exhaustive search, provided that exhaustive search is efficient, but let's assume that it is, right? So that's what I'm going to do. Okay. So the key thing is to show that the connected components of the clauses of the constraints which are not yet satisfied have size logarithmic, and this is the key thing to show, right? So okay, so why is this true? So here's the idea. So every variable which is not assigned must appear in at least one frozen constraint, right? Because if I think about which variables are unassigned, these are the frozen variables. And when was a variable frozen? Well, it was frozen when it appeared in like one of these risky constraints, right? So that must happen. Okay, so now I say, well, okay, so now, you know, this is some graph theory, but what you can do is you can sort of look at the second power of the line graph of the frozen constraints, and you can convince yourself that the connected components of the constraints which are not satisfied are contained in the connected components of the second power of the line graph of the frozen constraints, right? The reason is that, you know, I have these frozen constraints, and if a variable, if I have a constraint which is not yet satisfied, it must have an unassigned variable, and if it has an unassigned variable, it must be sort of, you know, hitting a frozen constraint, right? So the point is that, you know, a variable, a constraint can be not satisfied without being frozen simply because, you know, all of its variables can end up being frozen, but they can end up being frozen because of different constraints, right? They don't have to be frozen because of that constraint itself. So, you know, there can be some innocent constraint, which is, you know, like not heavy, but like, you know, everything it's sharing, right? All of its variables are in frozen constraints, and then this guy gets passively frozen, right? So because of that, you can't look at just sort of the line graph of the frozen constraints. You have to sort of look at the second power of the line graph of the frozen constraints, right? So this is sort of the point. Okay, so now okay, you know, you can sort of think about this, but the point is that now what I want to show is that, you know, in the second power of the line graph of the frozen constraints, every connected component has size order log n, right? And the way to do this is due to Alon. Or one way to do this is due to Alon. So a 2-3 tree is a set of vertices such that, you know, any two vertices any two vertices in the set have distance at least 2. So the reason we are doing this is, you know, this will sort of give us some independence properties. And moreover, if you add edges between vertices at distances 2 or 3, then this is going to connect T. And the reason that we are going to do this is, this will sort of limit the number of such structures we have, and this will control the size of the union bound, right? So this is what a 2-3 tree is. And now, if you use like a greedy argument, what it's going to give you is that if this graph G2F, if this has a connected component of size logarithmic, then you can also find a 2-3 tree of logarithmic size, right? Basically, you can do this greedy process where you have a vertex, you remove its neighborhood, then you take the first vertex, which is a distance at most 3, and then you keep on repeating this thing, right? And then this is sort of going to give you a tree of logarithmic size. I mean, I'm hiding some factors of delta here, right? There's some factor of delta that's hidden here, but delta you should think of as constant as compared to 1. Okay. The other thing is that I cannot have too many of these 2-3 trees. The reason is that the line graph has maximum degree delta, so the number of vertices at distance 3 is at most basically delta cubed. So the number of 2-3 trees of size L is at most delta cubed to the L, roughly, right? So this is sort of the numerology here. And now what we want to show is that in order to show that there is no connected component of size logarithmic, I want to show that there is no 2-3 tree of these frozen clauses of size logarithmic, right? And then I'll be done. Okay. So now the way you can show this is the following. You say, well, initially the constraints have violation probability P. They are frozen when the violation probability exceeds P prime. So the probability of being frozen is P over P prime, right? So this is like basically sort of Bayes rule. Maybe I'm cheating a little bit, but this is basically Bayes rule. And now you say, well, since the vertices in 2-3 tree have distance at least 2, so they depend on disjoint sets of variables. So all of these, frozen events are independent. So the probability of the 2-3 tree of size L being frozen is P over P prime to the L, right? On the other hand, I have delta cubed to the L trees of this form. So if I want to beat the union bound, I want, P prime to be, delta cubed bigger than P. So this gives you the condition that P prime is bigger than delta cubed to the P. And then, remember that in order to extend this to a satisfying assignment, you needed that P prime delta is less than or equal to 1. So if you put this together, this gives you P delta 4 less than or equal to 1. And this is exactly, the limit of this partial assignment method of Beck, where, Srinivasan had this result for the KCNF formulas with T to the K over 4. And this is exactly where the 4 comes, right? So there is a 1 that comes from the local lemma. And then there is the 3, which comes from these 2-3 trees. And indeed, this first paper of Moser, this intermediate paper between, 2 to the K over 4 and 2 to the K over 32, which was, this 2 to the K over 2 paper of Moser, the main innovation was replacing these 2-3 trees by some denser witness structures, right? And you will see, or maybe I won't have time to really go into all of the details, but you will see that, or in our paper, I can say that the main reason for the 7 is also using these 2-3 trees. So if you find a way to work with these denser witness tree structures, then, there is hope that, you can sort of push the 7 to something, closer to like 4 or 3 or something like that, right? So this is sort of like the takeaway message. Okay. So now, in the remaining 15 minutes, and, if you see on the bottom, I have like slide 20 of 32. So I'm like, clearly over prepared. But in the remaining 15 minutes, I will give you like some sense of, how we prove the sampling result. So this is sort of our high level approach to the local lemma, right? So this is counting local lemma. So this is very much inspired by Moser's approach. So what we do is, you say, well, first I'm going to generate the sequence of partial assignments that the randomized greedy algorithm gives me, right? So when I run this algorithm of Beck, it gives me some sequence of partial assignments. And then PS is sort of this maximal partial assignment, at which point, sort of all of the variables are either assigned or frozen and nothing is available. Okay, so I run this thing. And let's say that SPJ denotes the set of satisfying assignments extending the partial assignment PJ, right? So my goal is to approximate SP0, which is the number of which is the set of satisfying assignments extending the empty assignment. And like if you know this kind of thing, then like a natural thing to do is to just look at the telescoping product. So I can look at the telescoping product, and what's happening is that basically each of these guys is looking at in each of the factors, one more variable is being assigned, right? So basically this guy is yeah, and so one more variable is being assigned. So these are hopefully things that are easier to estimate. And okay, so now I have these ratios, and then I have this last quantity, right? And I want to estimate both of them. Okay, The last quantity is easy to estimate, and this is kind of the point of Beck's algorithm, that when I get to this last good partial assignment, I know that my formula is going to factorize into these logarithmic components, so I can just do like exhaustive enumeration, and I can tell you what SPS is, right? So now the main point is to sort of estimate these ratios, and the way to estimate these ratios is so this is sort of there was this method by Ankur Motra, and what we do is sort of we generalize this method, but the main sort of novelty is in the analysis of the method. And the point is that sort of on a high level, what's happening is that you have this analysis with 2-3 trees needed to sort of find the good partial assignment, and then there's also going to be an analysis with 2-3 trees which will let you approximate each of these ratios efficiently, right? So that's what's going on. And this is sort of the part of my talk which is sort of meant to be understandable. So now I sort of stop, and now what I'm going to do is in the next 6 or 7 minutes, I'm going to try to give like a very high level overview of like what the proof is, but this is going to be like a total disaster and completely ununderstandable, right? So I'll stop at like 55, let's say, right? So let's see what I can do in the next 8 minutes, but this is going to be bad anyway. Okay, so here's the idea. So my goal is to sort of approximate the successive ratios, right? So SPL plus 1 over SPL, where PL is like a partial assignment I got after L stages, and then PL plus 1 is a partial assignment I got after L plus 1 stages. So let's say VL is the vertex that was assigned a value in going from PL to PL plus 1. So this is basically saying, well, what's the probability that VL was assigned this particular value, right? Conditioned on like PL for the satisfying distribution for the uniform distribution and satisfying assignments. So of course, if I could approximate the ratio of all of these marginals, right? If I could say, well, what's the probability that a satisfying assignment assigns VL the value A conditioned on PL versus the probability of assigning VL the value B, then of course you could estimate the ratio SPL plus 1 over SPL, right? So now the idea is what you do is you kind of imagine this idealized coupling procedure for like VL assigned the value A and VL assigned the value B. And what you do is you sort of try to run a randomized greedy procedure again. You say something like, yeah, imagine that now I have this partial assignment extended by A and the partial assignment extended by B. And what I'm going to do is I'm just going to try to couple these assignments, right? And the way that you do this is you say, well, yeah, like again, I have some set of dangerous variables, assigned variables, and remaining variables. And initially, the only dangerous variable is VL, because VL is something that these two assignments disagree on. And now you do this, again, a randomized greedy kind of thing. You say, sort of let me look at the first unfrozen constraint, which goes between, like a dangerous variable and a remaining variable, right? And sort of, I choose like one of the remaining variables in this constraint, and I try to use the maximal coupling, right? And when you try to use the maximal coupling, I mean, my goal here is sort of to get these assignments to agree as much as possible. Okay, this is kind of this is not going great, right? So let's actually do this thing. Let me actually stop here and let me actually take questions, and that might be a better use of our time, right? Because this I can predict is not going to end well. So let me stop here, and I can take questions about like what this procedure is, and that might be a better use of our time. So I'll stop here, and I'll say like thanks for your attention. These are the references, and now I can go back and I can talk about the algorithm, and we can do an interactive session. So thanks and apologies for over preparing, but I hope you learned something from at least Beck's algorithm, if not ours. Okay, thanks.
So thank you, Vishesh, and yeah, please unmute yourself and then give Vishesh a round of applause. So yeah, if people have any question, maybe shorter ones first, and then questions to go through the last 15 slides only later, or
yeah, I saw Peter's face, and at that point I knew I have to stop because this is not going to go well. So yeah. Okay, so any questions? Yeah, I mean about like anything.
You said that there's some bottleneck in the analysis which helps you to improve this 7 to Can you somehow highlight what is the essence of the problem here?
Yeah. So I can sort of, you know, okay. So I can sort of, yeah. So this is maybe a question that's doable. Okay. So the idea is that, you know, recall that, you know, in this Beck thing, there was these thresholds. You know, there was P, which was the original thing, and then there was P prime, which was sort of your new tolerance, right? Now, what you do in this marginal computation, right? In the computation of the marginals, you also sort of run this randomized greedy process again, right? But kind of in a way, in sort of a different way, with like these new probabilities P double prime, right? So P prime is, you know, something that you've already kind of given up. You know, you could have constraints at this point which have probability of being violated, which is P prime. And now to do this marginal computation, you run this randomized greedy process again. So in order to have some slack, you need to work with like new probabilities which are P double prime. And now, you know, if you sort of do the same kind of computation, you'll see that, well, you know, P double prime should lose compared to P prime, and then P prime should lose compared to P. So when you chain this thing together, it kind of gets bad, and, you know, you get like this 10. So the correct way of doing this is, you know, I mentioned this two-step procedure, which is sort of first to compute this partial assignment and then to compute the marginals. But the correct way of doing it is sort of to combine it in one step, which is, you know, you're sort of finding the partial assignment in a way which will also let you compute the marginals, right? So the goodness property that you want is more. And now if you sort of do a martingale argument, what you can show is that this P prime can actually be replaced by P. So now you're only losing in one step, which is, you know, to go from like P double prime to P, and then, you know, the slack that you need for P double prime, right? So by being a little bit more efficient, you know, you can combine this and you can get a 7, but this is still not good because, you know, like we're still losing, you know, these like factors of like delta cubed in a couple of steps because of these 2-3 trees, right? So really sort of, I think the main thing to do is to sort of, you know, get beyond these 2-3 trees and, you know, sort of do something better. Okay. Now, I guess like one question which nobody asked, but, you know, since you know, this might be something to talk about, is you might say, well, you know, you showed this like, you know, sketch of this proof of like of Beck essentially, and you said that 2-3 trees get stuck at 4, but then you also had some result with coloring which got like a constant of 3. So how did you get like 3 instead of 4? Well, the reason is that, you know, when we work with colorings, you know, because you have this thing where only like a small number of assignments are violating the constraints, we're able to work not with partial assignments, but basically with like complete assignments of a projection of the problem. And since we're able to work with like a complete assignment of the projection of the problem, we are using not 2-3 trees, but sort of 2 trees, which are, you know, connected. Once you connect everything at distance 2, so you only lose like a delta squared as opposed to delta cubed there, and that's why you get a 3, right? But the problem, you know, if you know about these sort of algorithmic versions of the local lemma, is what Moser was able to do is he had this like idea where instead of like working with partial assignments and then extending them, what he was able to do was like use like a full assignment and then go at like, you know, these violating clauses and then resample them, right? So this kind of thing, you know, works for the existential version, and then you can build this witness tree and, you know, you can do this like entropy compression argument. But in the sampling point of view, right, like if you do like a full assignment and then you resample it, then like who even knows like what's happening on the level of the distribution, right? So that's why it's, you know, like kind of very complicated to sort of work with full assignment and then to resample it. But I still wonder if, you know, there are like denser versions of these witness trees that you can build and you know, which sort of help you do something better than, you know, the 7 and or 5 and, you know, sort of get you closer to this 2 NP hardness threshold, right? So that would be cool. I mean, another thing, which maybe that's not true, right? But like this hardness, this NP hardness with like K/2, this was like NP hard even for monotone instances, right? I mean, it could be the case that, you know, for like non-monotone instances, right, there is something better, right? Like this is like the NP hardness is okay, like K/2, and there is an algorithm for the monotone case, but it could be the case that, you know, the NP hardness is actually worse. And of course, you know, you don't know this until you've proved things either way, right? So like anything could happen, and, you know, this is sort of kind of open, but I guess like my hope in sort of giving this talk is that, you know, now we have like a lot of people in the audience here who do combinatorics, and this is like a relatively new problem. So hopefully, you know, there's some room to use combinatorial ideas and, you know, sort of work on this problem, which is, you know, still sort of relatively new, and, you know, there seems to be a lot of slack here. So yeah.
Yeah, Vishesh, thank you for an and that really is a lovely result. I like it very much. You went a little fast for me here and there, and way back when you were talking about the background, the results of Bizakova, Alanis, Goldberg, Guo, and Stefankovic.
Yep, right here.
Right. Okay. So this was for randomized algorithms?
I mean, yeah, so basically what they have is they have a reduction from these hard instances of the hardcore model to hypergraph independent set, right?
Right, but somehow I missed the difference between this negative result and the upcoming positive result of Herman, Sly, and Zhang.
Yeah. So what this result shows is that it's NP hard to approximately count the number of independent sets of a K-uniform hypergraph if the degree is if the degree is less than or equal to 2 to the K over 2, right? So okay, so I guess no. So okay, I see. So the problem is that I said okay, there's like a difference in constants, right? I think I should. So Peter, you see my point, right? So what this showed is that there is an instance where the degree is 100 times Q to the K over 2, and it's NP hard. What Herman, Sly, and Zhang showed, yeah. So this is like the usual sloppy notation. What Herman, Sly, and Zhang showed is that there is an algorithm where the degree is at most 2 to the K over 2 over 10, and then the Glauber dynamics mix first. So there is sort of a slack in the constant, and
that makes sense.
Yeah. Sorry, this was like like a bad way of like presenting this, but yeah, that's the idea. Yep.